Alright, so good morning again, everyone. Despite we already start the discussions of predicate logic last week, and turned out the quiz result is not too good, and we already agreed that this week we're supposed to meet in the class and have the face-to-face session. In order we can make it clear the things that you all seems not too clear or not too sure about how the predicate logic works. But as also promised, I'm still keep going to provide the lectures video first, and definitely I'm expecting that you should watch the lectures video before we make an appointment to have the face-to-face session, so that at least the things that you not really understand when you watch the lectures video can be discussed and cleared out during the face-to-face sessions. Okay, so again, despite the result of the quiz is not so good last week, let's just us run through first what we already have last week, so we know from which point we should start or we should continue the next lessons. So here some of the conclusions. The first one, as we already see in here, we did try to understand and see how propositional logic differs with predicate logic. So we already understand why propositional logic is not enough to describe properties and its related specifications. That's why we need another tools which is more powerful than just propositional logic. So as stated here, that the propositional logic is not enough to describe properties and its related specifications. Therefore, we come out with another tools in formal method which we call predicate logic syntax, that has more object or tools that can describe or represent what propositional logic doesn't have, especially when we talk or have the variables which is can make use to explain more detailed things, and then when we have the quantifiers to state about collections of object, all of them or part of group or part of object or some of them, and then we have the predicate to state about the things that we would like to explain in there, instead of using the alphabetic as we use in propositional logic. The fact in predicate logic we can make use that predicate as the one of the expressions, and then the rest of the connectives, they are seems all the same as how we have in propositional logic. Also, we have a collections of object which is called as a domain of a variable, and then as mentioned earlier, there are two kinds of quantifiers. There are universals to state of all, and there is existential to state of some or part of the group in there. And then the collections of objects satisfy the property Px. It's called as the domain of interpretations. And then we have this kind of symbols, a new one in predicate logic, which is we don't have in propositional logic, which this symbol is called as universals, and as mentioned also last week, it's always or most of the time it's related with implications. And then also we have here existentials, okay, which is notions with this symbol, which most of the time it's related with a conjunctions. And then also we discuss about negations of statement. As you see, this is the simplest thing that we can see. If we have negations for all x ex, then that will be equivalent if only if the negations of there is x ex. And then if we have existential or there is x ex negations, if only if the negations of for all x ex. So we did some of we already discussed about this also. One of the examples we did mentions in the previous one that for example, if we have not ex, then that will be equal to for all x. Then if we have not for all x, then it will be equal to there is x, like that. You may check the previous examples as how we did last week in the previous class. So the two things here that we not yet discussed last week is about the bound variables. Bound variable is the variable within the scope of the quantifier. Actually, we already used that in most of the examples, but we just not mentions how is it bound variable and how is it look like. So bound variable is the variable within the scope of the quantifier. Free variable is the one out of the scope. So we can see later on, after these conclusions, then we are going to look at that. And then a predicate well-formed formula is valid. Also, we haven't seen about the validity last week, so we are going to see that today. So it is valid if it is true in all possible interpretations. So I believe for this point, for the whether it is valid or not valid, it looks like it's the same technique to see how is it considered as a valid predicate logic expressions or not. Is the same things as how we do it in propositional logic. Okay, so I'm going to go through with few slides to explain or to show to you about the validity in predicate logic and how is it called is as a bound variable. Then after that, we are going to jump into few examples on the next video. Okay, so but before that, as I mentioned, so look at this one. So this is about the validity in predicate logic. So as you see, it's mentioned here. So it's similar to tautology of propositional logic. It's just that in propositional logic we call it tautology, meaning it is true for all possible model. But in predicate logic we didn't call as a tautology, but we call as valid. So it's just a different term. So in propositional logic, we call it tautology, and in predicate logic we call it as valid. So this is just a different terminology, but they are referring to the same things. And next, the truth of predicate well-formed formula depends on the interpretations. And then a predicate well-formed formula is valid if it is true for all possible interpretations. So it's the same things as how we have in the propositional logic. So in propositional logic, it's true if it is true for all row of the truth table. So it's a little bit easier for propositional logic because we can just check from the truth table. If it is all true, then it's considered as a tautology, which is a little bit different the way to see it in predicate logic. And then a valid predicate well-formed formula is intrinsically true. So this is also the same. Now this table just give us a summary, the different or the similarity between propositional logic and predicate logic. Okay, so let's just highlight the first one about the truth value. The truth value for propositional logic, the truth value true or false, it just depends on the truth value of the statement letters. Okay, however in predicate logic, the true, false, or neither if the well-formed formula has a free variable. So the way to see it is a little bit different, so we are going to check that later on through few examples. Okay, so it's not like you see here in propositional logic, it depends on the truth value of the statement letter. But here, whether it is true or false or neither, it depends if there is any free variables. So this is a new terminology about the free variable, but the free variable we are going to discuss after this slide is just to check whether the variables is bound or not bound into a scope of the quantifier. So we are going to check that later on. And then propositional logic, if it is intrinsic truth, then we call it as a tautology, meaning it's true for all truth value in statement. But just that, as mentioned earlier, in predicate logic, we didn't call that as a tautology, but we call it as a valid well-formed formula. And then the methodology to prove the validity, we can make a use truth table, but when it comes that the expression is complex enough or longer enough, then truth table might not be efficient. Then we know how to use proof sequence. We already done it. The proof sequence which use the 3 rules in there: equivalence rules, inference rules, as well as the deduction method. While for predicate logic, it seems not possible to use truth table, so we make a use proof sequence using the rules, the 3 rules as we also use in propositional logic. The rest of the technique or method to do the proof sequence is all the same. Alright. And then here also said that free variables. So this is what mentions earlier about the free variables. So free variable for all x p x y. Let me not because I want to hold on, yeah. Okay. So free variables here. So you look at these structures. So for all x, p x y implies there is y, q x y. So here variable y is not defined for p x y. Hence, y is called as a free variable. Such expressions might not have a truth value at all. So this is what we are trying to see in here. Because here we have quantifier for all x. So it states about x. But here for all x, p, x, y, the y here is not yet explained of any. Okay, that is why it becomes free variable. But it differs with the second statement here. Over here we have there is y, q, x, y. In this case, y is no longer become free variable for q, because it's already explained with the quantifier xy over there, as well as x. X also already explained with the for all x over here, like that. Okay, can't you understand that? Look at the bracket as well. So for example, if I just make it easy expressions, for example, I have like this for all x, and then I have big bracket here. So for all x inside this bracket, they are not free variable anymore. So for example, as I put it here, for xy implies q x y. Okay, so we see x on the p and we see x on the q. So x is no longer free variable because already explained with the for all x over here. But as you see, y is not yet explained. So that is why y become free variable in this case for both p and also q. But when we have there is y here So it makes this y over here no longer free variable, because there is y here, explain all the y over here, but not y over here, because it's already came before that. Before this there is xy. Okay, so I hope you understand how a variable become a free variable, or how is it become a bound variable. Okay, so let's take a look at the next one over here. So bound and free variables. Okay, so here state variables are bound if they are within the scope of a quantifier, otherwise they are free. So look at the next examples over here. Here, for all y, sister xy. So in this case, y is already bound with this one, but x is free because none. Also x over here, so x and x is free. So y is bound, x is free. The same variable may be bound and free in a different occurrence. So for examples, look at these expressions. So here we have for all x. So x here is bound already. And for all y, so y here is bound already. Okay, and then x here is also bound. But this over here is already out of the scope. It's already out of the scope for all y. The y here become free, but not x. Because for all x over here, the boundary is from this point up to this point, like that. Okay, can you see that? Yeah, if not, please write a comment, then we are going to discuss it again during the face-to-face sessions. So the next one, terms may be substitute for free variables. The substitute terms must not contain any variable that are bound at that point. Okay, so look at again here another structures. So we have here for all y, okay, and then we have bracket here starting from here until here. Okay, and then the for all y at the beginning here, the scope is from here up to here. So meaning whatever y we have to the end, that will be bound variable. But the z here is a free variable. Now look at the second expressions. Not for all y, sister, mother, y is all bound variable. Female, mother, y is all bound variable. Okay, so hopefully you can see that when is it a variable become a bound variable, and when is it become a free variable. All right, let's take a look at the next one. So this is some examples. We will go through this slide first before we have examples on the board later on. So validate examples. So if we're looking here, for all x, px, there is x px. So we said this is valid because if every object of the domain has a certain property, then there exists an object of the domain that has the same property. Or easy to say like this, you see this x is bound with this one, and this x also bound with this one. So there is no free variable here. So we call it as a valid. Over here, valid, quite obvious on the second one, since A is a member of object of the domain. So A here is no longer variable, it's a constant. So when it is constant, we doesn't need to state whether it is bound to what. As mentioned here, A is a member of object of the domain X, because it's already constants in there. It's already value, no longer variable, that not bound to into any. So this expression is also valid. All right. Now look at the third one here. There is xpx for all xpx. This one quite not valid, since the property cannot be valid for all object in the domain if it is valid for some object of then domain. Can use mathematical context to check as well. What this statement trying to say, let me just give an analogy. Here saying there is xpx implies for all xpx. For example, like this. You are now BSEM year 1, 17, not 17, you are 18, oh sorry, you are BSEM year 1, 18, you are 1801 kah? Okay, so let's see, I said student in the batch BSEM year 1 1801 has a formal method modules. Okay, so I said BSEM year 1 1801D has formal method modules. Okay, so if I put a statement, if BSEM year 1 1801D has module formal method, then all students in KIGS has formal method modules. How is it sounds for you? Something that applicable for small group, then we said it's also applicable for the big group. Is it true or false? So definitely no, because we do not know for sure if things that applicable for small things here also applicable for the entire group over here. No, right? But if we change the situations, if all KIGS student has to wear MIB dress every Thursday, then BSEM year 1 1801D has to wear MIB dress every Thursday. How is it? Something that a must for the big group, it must be also a must for a small group in there. This one shows by the first expressions over here. That's why it is valid, but different with this one over here. Okay, so this is some validity examples. Of course, this is a simple structures or expressions, so easy to check. But definitely when the structures become longer or more complex later on, then the way to check the validity is by doing the proof sequence. All right. Let's see what we have next here. Okay, also over here, it said invalid. This structure sets is invalid. Okay, so how we can check this? It is invalid. Now it says invalid can prove by mathematical context by taking px equal to x even and kx equal to x is odd. Okay, let's just read first. In that case, the hypothesis is true but not the conclusions. Is false because it is not the case that every integer is even and every integer is odd. So this is a very clear cut, yeah? Because when we said, for examples, if we define px, x is integer, then we said qx, x is odd, for examples. Okay, so when we take a number, for examples, for example, like p5 implies q5. We know that 5 is integer, true, and q5 is also odd, so it's true, right? But when we have x equal to 6, so px, sorry, not px, p6 implies q6. We know that 6 is integer, so it is true, but q6, x is odd, this is false. And we know when implies, when we have tf, then the result is false, so it is invalid. Okay, right? So I guess that is all for the validity and about bound and free variable, the one that missed from the previous classes. I mean, the explanation is missed there because if I'm not mistaken, on the last classes we only up to negations only on the predicate logic. So hopefully this missing brief or explanations about validity, bound and free variables is all okay. Then to make up what is missing last week, also some misunderstanding about the predicate logic structures, how we do the translation from verbal statement to predicate logic expressions. We can try to make it more details discussions during the face-to-face sessions on the next classes. Okay, so after this video, the next video I'm going to continue to the next discussions, which is hopefully by you watch through first, and later on during the face-to-face session, anything that you not understand, we can discuss further as well. But I'm expecting that you can pinpoint exactly on which part that you couldn't understand. All right, so that's all, and let's continue to the next video. Thank you.